Well, hello. This is Larry again, and I'm here to discuss the chromatic scale and go into a little more depth about it. The chromatic scale itself is basically playing every half step note, going up or down the keyboard or the fretboard if you're a guitarist. And so we're going to talk about the sort of the structure of that scale and where it comes from. So if you'll bear with me, I'm going to bring up a slide presentation, and we'll use that to proceed with our conversation. So let me bring that up. Okay, so yeah, you just heard me play the chromatic scale between middle C and high C. So that's a chromatic scale. You can see the notes of the scale there. The white keys C, D, E, F, G, A, B, C. And the black keys are the C sharp or D flat, C, D sharp, E flat, F sharp, G flat, G sharp, A flat, and A sharp, B flat. So before we get into the details, let's do a few definitions here because they're important to understanding the basics of where the chromatic scale, which by the way is that set of chromatic notes in all of the octaves of the musical scale are the fundamental basis for Western music. Almost all music is tonal and falls along that, where the notes of the songs are one of the notes on that scale. Now that's obviously not 100% true. There are pitch bends and things like that produce tones that are in between the regular notes, but the basics are those main notes along the chromatic scale. So let's talk about what a musical note is, and that is it's a tonal sound. It's one of the basic components of music, and it has three main characteristics: pitch, volume, and duration. And today we're going to talk about pitch, obviously volume, duration, how loud it is, how long it lasts. But the pitch is important for this discussion, and that's the quality of the notes that's characterized by the fundamental frequency, the audio frequency of that tone. And frequency is measured typically in cycles per second. It's cycles of the sound wave, and an official physics term for cycles per second is hertz. So if you hear me say hertz instead of cycles per second, I just mean cycles per second. And then, as you know, we've talked about scales and modes, and those are sequences. So the C major scale is a sequence of tones, and it's a sequence of whole and half steps. So it uses some of the notes, but not all of the notes on the chromatic scale. Something else that's important and very fundamental to what we're talking about is the fact that two notes that are an octave apart, and you can tell they're the same note, but just one's higher. Those notes are an octave apart. That their frequencies differ by a factor of 2. So A440, that's an octave above A220 and an octave below A880. Okay, and as I think sort of implied, that Western music is based on a scale that has been derived by taking the interval of an octave and dividing it into 12 intervals. So if I have 12 intervals that are bounded by an octave, I end up with, if I include the octave note, 13 notes. All right. So that's an interval. going from there to there. So here's 12 intervals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 13 notes, 12 intervals. And so I've mentioned the chromatic scale, obviously, a number of times before, and that is a sequence that uses all 12 unique pitches within the octave, going from the bottom note of the octave to the top note of the octave, or backwards, up or down. And that scale is referred to as being even-tempered. And we'll talk about what even-tempered means as we go along. In fact, that's sort of the heart of this conversation. So here are the frequencies of the keys on that scale going from middle C to high C. So you can see middle C has a frequency of 261.63 hertz. High C has a frequency of 523.25 hertz. The A in between has a frequency of 440 hertz, and so forth. So there are the frequencies. We're going to look at them in a list here. Well, first, but before we do that, let's. I'm telling you that those are the frequencies of the notes. Let's confirm that, and I'm going to do that with a little demo here. By bringing up a tone generator. Let's start with 261.63. Since this tone generator only accepts whole numbers for frequencies, I'm going to use 262. That should be close enough. Okay, oops, 262. And this should be middle C. And there's middle C. All right. We said high C was 523.25. So we'll run that down to 523. 523. We said A was 440. And just for grins, let's do D. I think we said was 293.66. So let's take 294. So now that we've done that, let's go back. And again, this is the set of tones and the frequencies. And let's talk about what even tempering means. First of all, you might say, well, the frequencies are evenly spaced, but clearly that's not the case. I mean, if you take the difference between 277 and 261, for example, the difference between the frequency of C sharp and C, you can see that's considerably different than the difference between, let's say, C above middle C, high C, and B. So the difference between 523.25 and 493.88 is considerably larger than that between 277.18 and 261.63. So the numbers are not, the frequencies are not evenly spaced. So what is even about even tempering? And here's where it gets only slightly geeky, and that is we have to use logarithms. If we look at the logarithms of those frequencies, and I'm using the log base 10, you get the following set of numbers: 2.4, 177 for C and 2.7187 for for high C. So there's your set of logarithms. And now if we take the differences between adjacent notes here, you find an interesting result. You get 0.0251. So the difference is that, or that the even tempering, what's even is the even spacing of the logarithms of the frequencies. And if you remember also from high school math, that when two logarithms add, so if you take the 2.4177 and add it to 0.0251, that's equivalent to multiplying whatever number that logarithm came from whatever number the other logarithm came from. So when logarithms add, their original numbers multiply. So the question is, what's the multiplier? And it turns out that the antilog of 0.0251 is 1.05946 approximately. So, excuse me. So it turns out that if you start out with the frequency of the C note, middle C, which is 261.63, and successively multiply that by 1.05946, you get each of the frequencies until you get all the way up to the frequency of high C at 523.25. So it turns out that that sequence of frequencies is what's called a geometric sequence. That is, it's a sequence of numbers that differ. Each number differs by a common factor. All right, so now let's because it's related, and it's kind of, I think, an interesting aside, but related to this. Let's talk about guitars for a second. You can play a chromatic scale on a guitar as well by sliding your finger up the fretboard. On the E and the low E string, you play it open and then play the first fret, the second fret, third fret, and so forth. You go E, F, F sharp, G, G sharp, A. You go up the chromatic scale. So, so let's talk about the physics of a vibrating string, which is the basis for a guitar. And the string's pitch, again, we're talking about pitch, depends on the thickness of the string, the tension of the string, and the length of the string. So the thicker the string, the lower the note, and so you know that the low E string is a fat string and the high E string is a thin one, and all the strings in between kind of vary in length, going from thick to thin. The tension of the string you set by the keys on the guitar, and so you tighten the string and that raises the pitch. You loosen the string and that lowers the pitch. And then finally the length. And you've probably noticed that as you go up the fretboard, the string gets shorter and the pitch gets higher. So it turns out that the pitch varies as it's inversely proportional to the length of the string. So so given that once you've tuned the guitar, the fatness of the string is fixed, the tension of the string is fixed, approximately fixed, because obviously when you press the string a little bit, that changes the tension very slightly, not significantly, but a little bit. But let's call that fixed. The thing that you're varying is you're varying the length of the string by pressing at a particular fret. So that means that if I have a string length, and I'm going to use one of my guitars has a string length from nut to bridge of 25 inches. If I want to know where the first fret should be, well, if I take, since it's inversely proportional, if I want the note to be 1/2 step higher on the chromatic scale, since that's a frequency that increases by a factor of 1.05946, I have to decrease the length of the string by a factor of 1.05946. In other words, I divide 25 by 1.05946, and I'll get the distance to the first fret. And if I keep doing that division, I get all of the lengths to the frets. So here's that table. And so Again, using the example length of my dreadnought guitar of 25 inches, if I divide by 1.05946, I get 23.6 inches for the first fret, 22.27 inches for the second fret, 21.02 for the third, and so on. And lo and behold, at the 12th fret, I get 12.5 inches, which is exactly half of 25. And if you recall, the 12th fret, that's the octave note. So when I'm playing an E on the 12th fret, I'm playing the E above the E that I play when I'm playing open. And you also probably recall that that point on the guitar is pretty much the halfway point between the bridge and the nut. And that makes sense because since the octave is a factor of 2 higher than the note that's an octave below it, then that means that the string must be half the length, which is the inverse of 2. So you get the 12th fret is at the halfway point, and it is there for the same reason as the chromatic scale is using that factor of 1.05946. The frets are comparably distanced on the fretboard using the same factor. Now there are some slight differences that are due to the fact that the vibration of a string in the ideal world of physics is not exactly the same in the real world, and there are some slight variations that are caused by the slight increase in tension, a slight change in the length of the string because of the angle when you press the string down and so forth. But all those things are kind of taken into account by the luthiers when they design a guitar. But these ideal numbers are very close to where the frets would actually end up on a guitar. And in fact, I did that measurement on my guitar, and if you notice that 25 inches from nut to bridge, and the third fret is right about 21 inches. So measure measure your guitar if you have one, and see if that works out about the same for you. That roughly that proportion. So we talked about notes and tones and pitch. That was the main thing. We talked about the pitch being the frequency. We talked about the Western scale being even tempered, and then that means that the chromatic scale is basically a set of frequencies that are a geometric series, a geometric progression. And it turns out that the distances of the frets on a guitar are approximately an inverse geometric progression. That is, the lengths are successively divided by 1.05946, that magic number. So that really concludes our conversation today. Next time, we'll probably go back to talking about one of the other modes. In the meantime, have a happy listen here, and I hope you're enjoying music in general. Okay, take care. Talk to you soon.